Okay, so today we are talking about limits again. I bet you thought those wouldn't come up, but they do, and they're randomly thrown into this chapter. And so without further ado, we are talking about limits at infinity. So this is 3.5. We have a few objectives. Problem set 3.4 is due. Homework is problem set 3.5. Lecture will be linked. I keep confusing myself with due because I think of it as like D-O. Maybe I should not include that, but either way. Limits at infinity is part 1. So in this section, we will consider the end behavior of a function. So in other words, as a graph of a function approaches infinity or negative infinity, what goes on? So we have a couple definitions that are pretty straightforward because we already are familiar with limit notation, thankfully. But limits at infinity are denoted by the limit as x approaches negative infinity of some function is equal to whatever it's equal to, and the limit as x approaches infinity of some function is equal to whatever it's equal to. So we have limits at both positive and negative infinity. And that's literally it for section 1. Part 2 is horizontal asymptotes. So as x increases without bounds, so as the x-axis approaches infinity, sometimes it gets very close to a certain value. And we can write that in math as the horizontal line y equals L. So we can see in this image as our x-axis is, approaching infinity, x is going on and on and on and on, and, infinity is somewhere way out there. So our x-axis is approaching infinity. Our function is approaching this horizontal line y equals L, right? So it starts here and then it's getting closer and closer and closer and closer. And it's assumed that as it goes to infinity, it approaches that, line. And we can write that horizontal line as the function y is equal to L, where L is whatever number it happens to be. And so that's the actual definition of a horizontal asymptote. So hopefully maybe your pre-calc brain is like, oh my gosh, cool. The line y equals L is a horizontal asymptote of the graph of f if the limit as x approaches negative infinity of f of x is L, or the limit as x approaches infinity of f of x equals L. So that is actually the value of our limit, because we can see that as x approaches infinity, so as our x-axis approaches infinity, our function is approaching that value. So our limit is equal to that value, whatever it is. This definition implies that the graph of a function of x can have at most 2 horizontal asymptotes, one to the right and one to the left. One as x approaches infinity and one as it approaches negative infinity. So here's a quick little theorem. Something that I'm sure you will all be glad to hear is that limits at infinity have a lot of shortcuts. And so once you are familiar with them by doing a lot of limits, you'll be able to crank these out. So this tells us if r is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r is equal to 0 all the time, every time, no matter what. And the same thing goes for negative limits that approach negative infinity. Limit also is equal to 0, always, no matter what. So that can be applied in a couple of instances. So we have a couple of examples here. And one thing that I do want to say that I don't think we quite capitalize as much as I maybe should have when we did limits is that limits follow a lot of the same properties as derivatives do. Well, I guess maybe I didn't because we didn't know derivatives yet, so I might be in the clear. But like when we can split up things across a plus or minus sign for derivatives and take the derivatives individually, we can do that for limits. When we can pull out a constant that's multiplied by a function to take the derivative, we can do that with limits. So for example, when we take the limit as x approaches infinity of 5 minus 2 over x squared, if we were going to take this derivative, we'd take the derivative of 5 and then of negative 2 over x squared. Same thing with limits. We can rewrite this as limit as x approaches infinity of 5 minus limit as x approaches infinity of 2 over x squared. And then we can just evaluate those limits. So the limit as x approaches infinity of 5, you probably don't remember this limit property, but as x approaches something of a constant, the limit is that constant. So the limit as x approaches infinity of 5 is 5. You can go back and check limit notes if you need to on that one, or you can take my word for it. And then minus the limit as x approaches infinity of 2 over x squared. Well, we just learned that the limit as x approaches infinity of c, if c is a real number, like 2, and r is a positive rational number, like also 2, then the limit of c over x to the r, or 2 over x squared, is equal to 0. So we know that our second limit is going to be equal to 0. So we're going to have 5 minus 0, which is equal to 5. So this limit is equal to 5. Easy as that. All right, our next one's a little bit less straightforward. We have the limit as x approaches infinity of 2x minus 1 over x plus 1. Okay, and so if we evaluate just the numerator, we can see the limit as x approaches infinity of 2x minus 1. If we plug in infinity, 2 times infinity minus 1, that does nothing because infinity is such a large number. That's just going to equal infinity. Or the limit as x approaches infinity of x plus 1. If we plug in infinity, infinity plus 1, you know, again, such a large number, it doesn't matter if we add 1, it's still going to equal infinity. So our limit actually comes out to equal infinity over infinity, which is an indeterminate form. So when a limit results in infinity over infinity, we refer to this as an indeterminate form. And notice this is one indeterminate form. There's actually 3, but we'll get into that later. And not even in this section at all randomly, but that is one of the indeterminate forms. And what you should do is divide the numerator and denominator by the highest power of x in the denominator. So we have 2x minus 1 over x plus 1. The highest power of x in the denominator is x. So we're going to have 2x minus 1 divided by x. We're going to have x plus 1 divided by x. This is going to equal 2x over x minus 1 over x. These x's go cancel, and then we get equals 2 minus 1 over x. Here we have x over x plus 1 over x. X over x is just 1. So over here we get 1 plus 1 over x. So now our limit we can rewrite as the limit as x approaches infinity of 2 minus 1 over x over 1 plus 1 over x. And then something cool that we can do with limits is that we can take these individual limits in our numerator and then divide by whatever that individual limit in our denominator. So if we go ahead and take the limit as x approaches infinity of 2 minus 1 over x, same thing as the problem we literally just solved, that 5 minus 2x squared. Limit as x approaches infinity of 2 is 2, minus the limit as x approaches infinity of 1 over x is 0. So it's 2 minus 0, which is 2. And then the exact same thing down here again, 1 plus 1 over x, limit as x approaches infinity of 1 is 1, limit as x approaches infinity of 1 over x is 0, 1 plus 0 is 1. So now our limit becomes 2 divided by 1, which is equal to 2. So this final limit is going to be 2. And then we have limits at plus or minus infinity of rational functions. And this is literally the key to the whole lecture. So this is all your homework problems right here, basically. If the degree of the numerator is less than the degree of the denominator, your limit's 0. If the degree of the numerator is equal to the degree of the denominator, the limit's the ratio of the leading coefficients. And if the degree of the numerator is greater than the the degree of the numerator is greater than the degree of the denominator, the limit doesn't exist. Memorize those 3 things and you will be able to evaluate infinite limits of rational functions all day, no problem, in like 2 seconds. And then we have another quick example about limits involving trig functions. So if we think about what the graph of sine of x actually looks like, it fluctuates, right? What is that word? I cannot remember it when it bounces between 2 values. Maybe someone else will remember and remind me in class. So as oscillates, as x approaches infinity, the sine function oscillates between 1 and -1. So therefore our limit does not exist. So for trig functions, you kind of have to think through what the graph might look like. We know that as x approaches infinity, sine bounces up and down, it oscillates. I'm so happy I remember that word. And so the limit does not exist. And then part 3 is infinite limits at infinity. So many functions do not in fact approach a finite number as x increases, decreases without bounds. So in other words, the limit as x approaches plus or minus infinity can also be equal to plus or minus infinity. And we can see that in an example like numbers 1 and 2, when we're thinking about the limit as x approaches infinity of x cubed. we know that the x cubed graph looks like this. And so we can see that the limit as x approaches infinity, that's going to be over here as x is approaching infinity, your function is going up forever and approaching infinity, okay? Versus as x approaches negative infinity, so as your axis is going to the left forever, our function is going down forever. So our function is approaching negative infinity. So that's what it means by saying like many functions do not approach a finite number. This x cubed function is not approaching a finite number. It's going either up forever towards infinity or down forever towards infinity. So the limit as x approaches plus or minus infinity can be equal to plus or minus infinity. And then we have another little example here. You guys aren't going to be as thrilled about this, but one way to evaluate each of the following limits, so 3 and 4, is to use long division of polynomials to rewrite the improper rational function as a sum of a polynomial and a rational function. So in other words, so that we can actually evaluate the limit without looking at the graph. So there's a quick little how to long divide polynomials reminder video with Sal Khan. And we're going to go ahead and do number 3 and 4 using this long division method. So if we want to rewrite our function, we have to long divide 2x squared minus 4x divided by x plus 1. X times 2x will get me 2x squared. So 2x squared, 2x times 1 plus 2x. You have to subtract it. So that's going to go to 0. This is going to be negative 6x minus 6. I'm doing this really fast, I realize, but that's why you should watch the reminder video. So you have to multiply by negative 6 to get a negative 6x. So then you have negative 6 plus 6. And then in your function, you have minus 6x plus 6. That should be a plus 0 right there. And then those are going to go ahead and cancel, and then this is going to become remainder 6. That was actually going to be negative. So then you're going to get positive 6 remaining when you distribute that, make those both positive. And then you get plus 6 over, which is your remainder, x plus 1. So we can rewrite this limit as the limit as x approaches infinity of 2x minus 6 plus 6 over x plus 1. And then in this, using this method, we can evaluate it piece by piece, right? Limit as x approaches infinity of 2x is going to be infinity. Limit as x approaches infinity of negative 6 is going to be negative 6. The limit as x approaches infinity of 6 over x plus 1 is going to be 0. You're going to get infinity minus 6 plus 0. Subtracting 6 from infinity is nothing because infinity is so infinite. So our answer, infinity. And then for number 4, it's going to follow the very similar lines except for with negative infinity. So that is infinite limits and horizontal asymptotes randomly thrown into the middle of 3.5. Yeah, I hope you all enjoyed.